Okay, we are back at the DNP presentation, finishing up here with possibly the last part. And the next layer we're looking at in the DNP message is the application layer. So if you were to look at your breakout sheet and follow it down from the data link header on the top to the next line down, the first thing we covered there was the transport header. And now we're working on the application header that's corresponding to the application layer, AH. So if we go back, we had data link header that was working with frames. We had the transport header that was working with segments. When it comes to the application header, we're working with something called fragments. So now you'll see that we have a fragment sequence number associated with the application header. We had a segment sequence number when associated with the transport header, and we were working with frames, and the size of the frames is a length byte for a data link header. So involved in the application layer is we're at the point of the message now of which all the other layers, the data link layer and the transport layer, was basically just responsible for moving the message through the network and delivering it to the right location, if you want to call it that, and confirming service and responses and logical links and all that kind of stuff. When it comes to the application layer, this is where now we're actually like a function code with Modbus, we're specifically looking at reading or writing a data type, freezing it, operating it, and things of that nature. This is where we're actually taking action on a specific object or data type, and that's the application layer. So when it comes to our requests and responses, we're working on one of these data types, right? Whether it be DIs, DOs, AIs, AOs, counters, or accumulators, or our all-encompassing class data, of which you know class 0 is our real-time or static, and class 1, 2, 3 now is our event data. That's our all-encompassing data type that really improves our efficiency of this protocol. So when it comes to requests and responses, we're looking at a specific data type or a class data type being requested from a server. Or we're looking at writing a value to an analog output as a set point or a digital output as an on-off value. Okay? So when we look at the application headers, where we're going to find the reading and writing functions. We're going to find the direct operates and the means of setting values to a set point or on-off controls. We're going to see the freezing operations where we freeze a value when we have something going on of where we want to record a specific snapshot of conditions at that time. And then, of course, we have the means of synchronizing clock by writing time and date to devices to make sure we have a synchronized event time across your whole network. So that's really what's going on at the application layer. Okay, now here, guys, and you'll notice this on your breakout sheet, and I'll mention it in a moment here, and we'll actually look at the breakout sheet in a moment, and I'll show you where this is shown. But this is a really important point that we have to understand, is when it comes to a request, the application layer is 2 bytes. So notice how here we only have 2 bytes. But when it comes to a response header, this is where things change. Now we have 4 bytes for our application header. And the reason being is because we have an additional 2 bytes of what's called internal indicators. So it's in the application layer or header that a server, when it's responding, will add 2 more bytes to give the master some indicators of what's going on at its end. So things like restarts, it'll indicate there's been a restart of the device. If if that's been the case. So it's just where the remote or the server returns other bits in the application header that are giving kind of statuses or an indication to the master about, you know, some of the conditions that are present at the device itself. So that's called the internal indicators. IIN bits is what they're called. So that's what we have in the application layer when we have a response is 4 bytes. If it's a request, there's only 2 bytes. So when it comes to the 2-byte application header for a request, let's look at the first byte. And the first byte is where we find this information right here. And if you were to look on your breakout sheet, you would see this corresponds exactly to that. This is indicating whether it's the first and final fragment. Now, fragments are really huge in number for bytes. So I think, if I remember correctly, a fragment is all the way up to 2048 bytes. So I think, as you can imagine, it's not very often that we're sending a request that's other than the first and final fragment here. So that's what those first 2 bits are, just like in the transport header. It's the first and final fragment, and then there's a fragment sequence number that requires 4 bits here. And then it's simply indicating, do I actually want you, am I actually confirming what you, the confirmation you were looking for at the application layer? And if I am confirming it, then I have a 1 there. If I'm an unsolicited message, I have a 1 there. You get the idea. It's the 1 that indicates that flag is set or that it's on. So unsolicited would be for those unsolicited messages we had talked about before. Application confirmation are both of these are in responses. So in a response is where I'm indicating that I'm looking for a confirmation at the at the application header, and that happens when a remote or server sends its events back to the master. It needs to know the master has received those events, and what it will do is it'll be sending back a 1 here saying, I'm looking for an application layer confirmation here that you've received these events. And once it does, then it can clear its event buffer. So that's what you see going on here. If we only have 4 bits to indicate our fragment sequence number, that means those are numbers 0000 through 1111, and that's 0 through 15. So once it comes around, if you were to have these large messages and the sequence would come around to 15, then the next one would just roll over to 0 again. So it's just a revolving sequence number that goes in here, fragment sequence. Okay, so if we take a look here, then we can see in our example in the request where we were indicating the application header. And the first part, or the first byte of that application header, is C2. So in order to interpret it, we break it out into its binary value, of which we know this will equal C and this will equal 2. And we take into consideration each and every bit in that 1 byte of information. So what is this saying? It's the first and the only, because it's the first and final fragment of this message. And then here, the sequence number, so the segment sequence number is equal to 2. So it's the second fragment sequence. So it says it's the only 1 fragment, and the fragment is sequence number 2. Okay, but that's only the first byte of the 2-byte value. So now if we go to here, to the second byte of the 2-byte value, because remember, we're breaking this down into its boxes, and we know for a request application header is 2 bytes long. So if the AH, or application header, is 2 bytes long, we're making 2 empty boxes of 2 bytes. This one's being the transport header, which we've worked with already. This is the application header. So when we look at that, we've already covered the C2, indicating it was the first and final fragment and fragment sequence number 2. But now is where we actually get to the function code. What is it we're trying to do here? And in this case, we can see we have a 0, 1. Now, if you simply look up on your breakout sheet, you'll see that 0, 1 is a read. So it means that with this master request, we're looking at reading some object. Okay, so how will we know what object that is? Well, we'll have to go on to the object header in order to determine that. But here, there's no doubt we're looking to read. But notice how some of the other operations here that we have the write function, of course. We have a direct operate function. Notice how we have freeze functions, both with no acknowledgement and using acknowledgement. And if you go through, you can see there's a number of other different operations that can be done. And that's what makes it a true SCADA protocol, is the versatility in all of these functions. Okay, so just give you some idea there. Read, write, select before operate, direct operate, freeze commands, freeze and clear, cold restart, warm restart of the device. So it gives you a really a good idea of what goes on in the application header when it comes to the requests. So now, if we take a look at the response, that means this is now 4 bytes, right? So we have a first byte here. You have a function code again, and that's the same as what we saw with the previous application header for the request. But here is where the difference comes in, is we have internal indicators, those IIN bits that I talked about. So when we look at the first byte, notice how it's formatted the exact same way. First and final fragment, say no confirmation, not an unsolicited message, and then some number in here. Let's say it's 0, 0, 1 to be fragment sequence number 1. But that's the same thing as what you see for the first byte of information. Now, when it comes to the function code, there really is only 2 or 3 function codes when it comes to a response. Okay, unsolicited response has a function code of 82. Rarely going to see that, of course, based on, I doubt if you'll be working with unsolicited responses or quiescent networks. So chances of you seeing that are slim to none. But this is the one that you'll see all the time. And that is simply a function code saying, hey, this is the response to your request. Because it's not, remember, function codes are operations, and the server isn't asking the master to, not usually anyways, to do an operation. So in this case, it's just saying, hey, here's your response. I'm identifying this as a response in the function code part of the application header. Then you have your 2 bytes of internal indicators. So here you see the 2 bytes of the internal indicators, and you see the same thing when you look at your breakout sheet. Now, I'll tell you once again, you're not required to define any of these bits or flags in these internal indicators. For the purpose of our course, all we need to do is be able to, once we see the raw information here, we need to be able to put the bits in their proper locations and then understand that, hey, we have a need time flag that's high, or a restart flag that's high, or a class 1, 2, 3 flag that's high. That's really all that you're required to do. If you wanted to know the definition of each one of these internal indicator bits, or these IIN bits, you guys know you could go to DNP.org and you would find a full description of what each one of them means. Okay? essentially, just to give you a few of them, if the device has restarted since the last time you polled it, then you would have a restart bit as a 1 here. And that would be telling the master, hey, I restarted, so I may have missed some events, or there may have been something going on that I missed, because I want to let you know there was a restart that happened. If the device control was put into lockout or into local mode, where you couldn't do remote operations, then this flag would be set, and it would be telling the master, hey, no use trying to trip any breakers or close any valves or do anything like that right now, because I'm in lockout or local. Need time is an example of where the server has lost its time, possibly from a restart, where it's just going to come up with a default time start, and it needs to have the master synchronize it again. So it's looking for synchronization, and then of course you've got your classes for your event data, 1, 2, 3. So if it was a class 1 event that was being reported back, this flag would be set. If it was a class 2, this flag, and so on. So that's what we have for an example of some of these internal indication bits. Okay. So again, as far as you're concerned, you just need to know where to place the 1s and 0s and how it indicates one of these flags being on. If you wanted to define it, you know how that's done. Okay, so let's look at the response here and this 4-byte application header. So notice how now we've targeted 4 bytes because we know this is a response. So when it comes to a response, we know it's a 4-byte value that we need to work with. Okay, so the 4-byte response application header. So here we see it from our example. Notice how we're into the response here now, whereas previously we were looking at the shorter request. Look at the size of this response because of course it includes object data, so it's a large message with multiple data blocks. So anyways, we're looking at the application header, and the first thing we're going to look at is the first byte of information, which is the E2 value. So if you convert E to binary, you're going to have 1110, and if you take 2 and convert it to binary, you're going to have 0010. So again, following the same format, that's indicating it's the first and the final fragment. This guy is looking for confirmation. Now it's interesting, we see this as a 1 saying that the remote is actually looking for confirmation from the master. And the reason why is I can guarantee you there's events in this response. And because there's events in this response, this is the remote saying, is requesting confirmation at this layer. And it wants confirmation so it can say, okay, these important events have been received by the master, and now I can clear my event buffer and start recording new events. So notice how it's looking for confirmation, and that's indicated by the 1 here. Then, of course, it's not an unsolicited message, so that's a 0, indicating it's not unsolicited. And then you have your fragment sequence number, of which is 2 here. Okay, so notice how that fragment sequence number, it's not an unsolicited message. This is looking for confirmation, and it's the first and only fragment. Okay, now we move on to the function code. So that's going to be this part of that 2-byte value to start off the response header. And we said there's really only 2 or 3, and this is the one indicating, okay, this is a response. I'm responding to your request. Perfect. Now where are we going? We're going into the 2 bytes of internal indicators. So if we take the value here, it seems like in this case there's only 1 bit that's set, or 1 flag that's been set. And the way you determine which one that is to convert all this to binary. So this in binary is a 1, this is a 0, this is a 0, and this is a 0, of course. So we've taken the value and dropped it down into its empty boxes, and the only thing we find is a single flag set, which is a need time. So notice how here it says the remote needs to be synchronized, right? It's saying, hey, I lost my time. I just restarted or something like that, and I need to be synchronized. Now, you may say, well, if it just restarted, wouldn't this be a 1? And you're absolutely right. It would be a 1 if it was the first message after restart, but it's quite possible it was still needing synchronization even after it indicated that it restarted, if that makes sense. So in this case, it was a message after that was indicating that, that it was looking to be synchronized. Okay, so let's actually go to that breakout sheet, and we'll just kind of look further at how to use it with respect to the application. So if we're looking at the breakout sheet here, remember we're looking at the application header section, and so if we look at the application header here, notice how when it's and if you look closer, right? If you look closer, notice how it says for a master application, that is a request header, notice how we only have 2 bytes. 1 byte, 2 bytes. And when we look at wanting to interpret the first byte, we just follow what we see here. That's 8 bits, and we follow the value in binary and drop it into each one of these boxes, and it'll allow us to determine all of those values, right? Then if we look at now the application function code, we just follow this arrow down, and this is where you find your reads, your writes, your direct operates, your cold restart, warm restart, and so on. That's where we find the function code. And if we're talking about a request, that's the complete application header. There's no more information to be found. But if we're looking at the response application header, we have to understand we're talking about 4 bytes of information. So we're following this over to here. The application control byte is interpreted the same way, so you just go back to this same thing. The application function code is one that comes from this table, because there's only 3 values you're going to find in a response: confirmation, the response, and then the unsolicited response. And like I told you, I don't think you're ever going to see that in power systems. And then we have our 2 bytes of internal indications, right? So what it means is our first byte is interpreted this way. Our second byte you follow down and interpret this way. Notice how this is that need time bit that we had set in our example there. So this is the way you use this, guys, is to just follow your breakout sheet to take the information as a hex value and convert it to binary where it's necessary in order to determine the flags that are set and things like that, to determine or interpret the meaning of the message. Okay, we are looking at the object header now, and this is really where we're down to the part of the message where the request is saying what are the specific objects that it's wanting to read or write or direct operate or freeze. And in a response, it's where the actual object group numbers, variations, and point data is being returned or coming back. So remember, even though there's class data requests, that is to say a class 0 for all real-time data, a server is not going to respond with a class 0. It's going to respond with the specific object group numbers and variations in its real-time database and give all of it for a class 0 request. So what we need to understand is things like class 0 for real-time and class 1, 2, 3 for event data. Those are only found in requests because that's a generic request for for whatever the server has, and what the server is going to respond with is very specific object groups and variations. I figured that was worth mentioning. Okay, so we're talking about the object header, and we're saying, okay, what is it that you want? What is the object you're requesting? What is the object you want to write? And this is all found in the object header. So if we look at the object header, the thing is, we can't say that an object header is the same size on every request or every response. And it's kind of unfortunate that way because it kind of complicates things. But this will kind of demonstrate it. If you look at an object header, there's no doubt we only use 1 byte to represent the object group. Okay, so that's for every object header. We only use 1 byte to indicate the object variation. Both of those can be looked up in your object library. That's the same for every object header. We have a 1 byte qualifier. Okay, that's a 1 byte value. That's the same for every object header. This is where things can differ, because when we're talking about what's called the range field, that can be from 0, that is to say it doesn't even exist, there is no range field, or all the way up to 8 bytes to actually say what we want to say in the range of points being requested or returned in a response. And this is where things kind of get somewhat complicated. But probably the easiest way to kind of relate to why this is what it is remember in DNP, we don't just have to ask for points that start at an address and end at another address. You could say like Modbus with its start address and number of points. You could ask for a list of points. You could ask for a range of points. You could ask for points starting at one address and ending at another address. There's multiple different ways of which you can ask for data. And you could even ask for specific point numbers and point values as a list, one at a time. Point 15 in your DI. 0.2 in your AI, 0.3 in your analog output table, and so on. You can ask for data in that way. It's that versatile, and that's what makes this, I guess you could say, a lot more complex. Is this object header when you're doing that type of thing, right? When you're asking for a list of points and so on. I would say most commonly, what you're going to find, and you'll see why once we start looking at messages directly, is this qualifier right here, and that is for all points. And when we're looking at a qualifier for all points, it's really very simple, and that's really means there is no range field. If I'm looking for all points, I don't need to indicate where to start and where to stop because I'm asking you for everything. So when it comes to a 06 qualifier, that's what you're going to see most commonly in a request, and it's dead simple to work with because there is no range field. And as soon as we see 06, we know that. Okay, so, and by the way, guys, if we look down here at the bottom, this is where we have our object header in our request message that we've been looking at. And if you line this up for byte by byte, here's the first byte that would go there, here's the next byte that would go there, and the 06 would be the qualifier here. Now, because I said for qualifier 06, there is no range field, then that means there is no more of the object header to deal with, and you've only got a 3 byte object header like what we see here. This is only 3 bytes. Okay, so once we start looking at that and examples, then hopefully that'll make a little bit more sense. Remember your variations, guys. You've got variations for each object, right? Variation 1 is a 32-bit analog, variation 2 is a 16-bit analog, Variation 1 for binary inputs is without quality flags. Variation 2 is with quality flags. Right? So this is kind of a summary of it all. And what do you see? The object group number, you look that up in your object library. Object variation, look it up in your object library. Qualifier, if you look down here, the qualifier is going to be indicated by this 1 byte value right there. And I'm going to actually show you a shortcut in on your breakout sheet to deal with this. But qualifier, you break it out into the first 3 bits that are indicating a value of 0, 1, or 2, and the second 4 bits that are indicating a value of 0, 1, 6, 7, or 8. Those are the only combinations there. And then those actually indicate the size of the range field, right? So think about it. If you were indicating a 1 byte start address and a 1 byte stop address, how many bytes would that take to represent that? 2 bytes. A 1 byte start and a 1 byte stop. If you were to make a 2 byte start, sorry, I should erase that so you can see it. If you were to be indicating a 2 byte start address and a 2 byte stop address, that's what indices means, is an index or a point number. If you were to do a 2 byte start and a 2 byte stop, what would be the size of the range field? Meaning, what size would this part of it be? Well, 2 plus 2, you would have a 4 byte range field. Okay? Now I talked about the 06 qualifier. We said it had no range field, so notice how this says 0. This doesn't even exist for a 06. A 06 has no range field. And therefore this wouldn't even be there. There would be no range. Then if you look lastly here at 7 and 8, what is 7 saying? A 1 byte quantity. So what you're saying is, out of your, say, analog input table, I want 6 points. Well, if I only need 1 byte to represent that quantity, then that means the range field is only going to be a 1 byte value. What about a 2 byte quantity? Well, then if I'm going to use 2 bytes to express the number of points, it will be a 2 byte value. Okay, so this describes the size of the range field. Okay, so that's really what we've talked about previously. When it comes to 0, that means there's no index. We have what's called packed data. So notice how a 06 qualifier was indicating 0, and the data is just going to be packed one after another. So that means to say there'll be no point numbers in what's returned. It'll just be, it says right here, point numbers will not be in the data field. If we've got a 1 as our index, then we're going to have values of a 1 byte that can be handled by 1 byte, which is 0 through FF, or 0 through 255. A 2 byte value is going to be points 0 through a maximum of all Fs, so 0 through 65535. I think you're kind of getting the idea there. And if we look at a 1 or a 2, because remember this is a 1 byte index, right? If we're looking at a 1 or a 2, notice how when the data comes back, it's going to be saying, okay, I've got a 1 byte to tell you the point number. So this is a point number. This is the data. So this is the value of a 16-bit analog or a 32-bit analog, whatever it might be. But what we're saying is with a 1, which is a 1 byte index, there's only going to be a one byte to represent the point number. If it's a 2 byte index, that means there's now going to be 2 bytes to indicate the point number. Right? There'd be 2 bytes to indicate the point number. And then we'd have point data after that, the value of the 32-bit register or whatever. Okay, qualifier 0, 0. That means there's no index, right? So that means there's no point numbers. And we have a 1 byte start and a 1 byte stop. So notice how this is a qualifier 0, 0 in the qualifier field, but the range field is a total of 2 bytes, just like we saw, because it's a 1 byte start address and a 1 byte stop address. What do we notice here? Well, if we have a qualifier 0, 1, it's a 2 byte start, 2 byte stop, and then we would have a total of 4 bytes. This would be a 2 byte start and a 2 byte stop. Now guys, here's something I'm going to mention right now, and it kind of goes back to something we talked about earlier. Do you remember we said that any 2 byte values are flipped? So it means, here's an example of where a 2 byte value would have to be flipped. So what it means is the least significant byte of the number would be here, and the most significant byte would be here. So let's suppose that it was a 2 byte value saying that you wanted to start at address, start address equals 6 base 10. So that's 6 decimal. Well, then you'd have to look at the hexadecimal value for 6, which we know as expressed as 2 bytes would be 0, 0, 0, 6. But what would that actually look like as the raw message? Remember, it would have to be flipped. So it would be 0, 6, 0, 0. And in order to interpret it, you'd have to flip it to understand that that was a start address of 6. Right? So this goes back to any 2 byte values are flipped, and this is an example of a 2 byte value as a start and stop address. Okay? Those are some of those things that can really get you. So when it comes to that 06 qualifier, we know there is no range field. What is the size of the range field, it says here? Well, the range field is 0 bytes. There is no range field, right? So don't forget that when it comes to a 06 qualifier. Okay, so remember I said I was going to show you a shortcut that can be used from your breakout sheet. You'll find this table on your breakout sheet. And just like we had the data link control byte table to summarize the meanings of qualifiers, it's the same idea with this table. It allows you to just go directly to this table and not kind of break it down into all its individual bits. So let's take, for example, our qualifiers are all listed here. Okay. Now these qualifiers all being listed here can be expressed as a 1 byte value, and we know that the qualifier in the object header is only a 1 byte value. So all of this can be expressed with 1 byte. But then what we see is the range field here that will be the result of a specific qualifier. So again, this is a review, but I'm going to make it quick. 8-bit start and stop means the range field is going to be 2 bytes. 16-bit start and stop, range field will be 4 bytes. A 06 qualifier, we know there is no range field, and that's how come this is 0 bytes. What happens if you're looking for a number of points that can be expressed with a single byte? Well, then that would be a 1 byte quantity. The range field would be 1 byte, and in that would be in that 1 byte would be indicating the number of points that you want to read or write. 2 byte quantity, 2 byte. 1 byte index and 1 byte quantity. 1 byte index and 1 byte quantity is a 1 byte value. 2 byte index and 2 byte quality is a 2 byte value. Okay, so yeah, that's a summary of the qualifiers and how they affect the range field and where they're used, right? So notice how over here the 0, 0, and 0, 1 qualifiers is a range of static points or a single point with a point number. So when it comes to using that in a request, you're specifically asking for a range of points or a specific point. And what would come back is real-time objects being reported back if you use that qualifier code in a response. So remember, these qualifier codes can be used in a request or a response. Here's a perfect example. When you're looking for all points from a specific class or a specific object, you can request it as a 06 qualifier and you're looking for all points. But notice how in a response, this qualifier would never show up in a response, because you're not going to say this is all points. You have to be very specific and to say this is point number 1, point number 2, point number 3, or a range of points or something like that, so that it's understood what data is corresponding to what point. So that's where you're never going to see a 06 qualifier in a response, because what has to come back is specifics. There's a general request for all points going out. There's specific values coming back in a response. So a 06 is another example of kind of generic, all-encompassing request. Okay, guys. So I guess I'm going to kind of leave it at that for now. We'll explore this a little bit more when we look at examples, and that's what we'll be doing next. But that'll be my last and final presentation, is to look at object header examples, and then we'll do some exercises. But for today, that's it.